So let me now move on to discussing propagators. So first, let me just tell you what propagators are. So formally, propagators are solutions to the wave equation with a source. So if you have some wave equation, and suppose delta is some wave operator, it could be the D'Alembert operator, it could be some other operator, such as the operator that is on the constitutes the Schrodinger equation. And suppose we have some wave equation like this. Now, if I consider the equation where on the right-hand side, instead of 0, I have some source. And by delta, I mean a unit source. It's kind of heuristically representing a delta function, a Dirac delta function. I could have written 1, but of course, since I'm dealing with functions, it's more sensible to write this as delta. So this G can be thought of as the inverse of this wave operator delta. So G, it can be thought of as delta inverse. Then G is an example of a propagator. In mathematics, these functions are known as Green's function or Green's functions. So let's first discuss the non-relativistic propagator in the context of quantum mechanics. So how do we view propagators in non-relativistic quantum mechanics? So the way we look at them is that suppose I have a wave function at some time t prime, and I have its spatial dependence. And I want to figure out from this data what the wave function will look like at a future time. So the wave function at a future time x, at a future time t, and at the position x is given by the initial data wave function and then integrated over all of space. So I'm looking at one dimension for convenience. And then times a function which propagates our initial wave function to a future wave function. So this function which propagates this initial wave function to a future wave function is known as the propagator. And formally, the propagator is the position space or position representation of the time evolution operator. So this is formally what the propagator is. Sorry, that should be an X here. Right. So if I draw a physical picture of this scenario, what I see is that I have time going that way. So this is time. And space is going in the horizontal direction. So at some initial time, say t prime, we label space coordinates by x prime. And at some future time, say t, we label space by x. And what we have is that we are given the initial value of the system at time t prime, which means that we know what the value of the wave function is along x prime at t prime. So this is psi x prime t prime. And so what we want to know is that we want to know what is the value of the wave function at some future time t and at some point x, spatial point x. So we want to know what psi of x of t is. And what this equation is telling us that the value of the wave function at a future time will depend on this initial data, as well as how the system propagates forward in time. And the way the system propagates forward in time is encoded in the propagator. So what we can see is that we can see that this future wave function psi is the propagator weighted with the wave function at different positions. So to make this a little bit more clear or clearer, what we can do is that we can take as our initial wave function. So we can take our initial wave function psi of x prime at t prime to be a delta function. So if you take this as, say, delta of x prime minus x0. So what this means is that we're taking the wave function to be localized at some spatial point, which we are calling x0. Now, if I plug this into my formula for what the future wave function will be, then psi of x of t is given by the integral over dx prime k x times x and t x prime t prime, and then we have the initial wave function at x prime and t prime. But instead, what we will use is that in its value is given by this guy, so we are going to use here the delta function. So we're going to use delta of x prime minus x0. Now, because we have a delta function, we can do this integral easily, and then this becomes k of x t x0 t prime, or so the 0 should be over here. So what we've shown is that the propagator is the wave function when your initial wave function is a unit wave function. So this is the general discussion of the non-relativistic or just a general propagator. So we saw that for the free particle, the non-relativistic case, the propagator was given by, I'm choosing the initial time 0 just for convenience. So one thing we can note here is that this is non-zero for whatever value of x and x minus x prime we have compared to t. So if you're looking at points which are spatially separated or space-like separated, we see that the non-relativistic propagator is still non-zero. Now, this is not surprising given that in non-relativistic physics, in Newtonian physics, the maximum speed at which signal can propagate has no upper limit. So even if we consider two space-time points which are space-like separated, they can communicate via the propagator. So let's move over to some relativistic propagators. So we can generalize to relativistic propagators. If you recall, the derivation of the propagator that we just saw above had a point where we were using the Fourier integral theorem to express the wave function at a future time in terms of the wave function at a past time, and it involved an integral over p where I had the usual Fourier factor of plane waves, as well as a factor which came from the time evolution operator. So in the non-relativistic case, this was minus I p squared over 2m. But for the relativistic case, we can replace this by the kinetic energy of a free particle, which is given by square root of p squared plus m squared. And then we have our initial wave function at time 0 and at x prime. And then we integrate everything over p and dx prime. So this is the formal expression for a possible relativistic propagator. Now this is an integral. The integral over p is something that we can do exactly in this case. However, it is useful and instructive to develop some intuition about how to deal with such questions in a more qualitative manner. So we don't want to do the integral exactly, but we want to develop some heuristic tools. So because the integral is over some phases, one thing we can do is that we can approximate this integral by taking the value of p such that the phase here is an extremum of the argument. And that what that means is that when we integrate over all p, all the phases near the extremum or the critical point, they will vary very slightly from each other. And therefore, they will interfere constructively and they will constitute the majority contribution to the propagator. Whereas the values of p, which is away from the critical value, the phases will change much more rapidly, and therefore they will tend to interfere destructively. So how do we find the stationary point or the critical point of the phase? Well, that's quite easy. What we do is that we take the argument of the exponential, which is, say, px up to I, minus square root of p squared plus m squared times t. Oh, there's a t here that I forgot. And then we say, we take its extremum. So we solve this equation. And once we solve this equation, we find that the stationary point of p is I of xm divided by x squared minus t squared square root. By the way, I've also put x prime equals to 0, just for convenience. So once we do this, we can now put this back into our integral, and then the dominant contribution to the integral to the propagator will then be from it'll be e to the power I by h bar. Sorry, I'm not being very considerate about h bar, keeping it or not keeping it, minus, let me just put h bar equals to 1. Then we have I px minus I square root of p squared plus m squared times t times some constant factor. So we are interested in evaluating this propagator in the limit when the 2 points that we're dealing are space-like separated, that x squared is greater than t squared. So since we're interested in evaluating this in the asymptotic limit in which x goes to infinity, we can see with a bit of calculation that I'll leave as an exercise that k asymptotically looks like e to the power I m square root of x squared minus t squared. So, this is non-zero. So we see that the obvious generalization of the non-relativistic propagator to the relativistic case still gives us a propagator which is non-zero for space-like separation.